Okay, we can get started. Good morning. Welcome to Operating Systems. My name is Surendar. How many of you are new to the department and this is your first class? Okay, so welcome to the Computer Science department. So there's some of my contact details. I have some office hours, but in general, if I'm in my office and you need talk to me, drop by. If I'm busy, I'll let you know. I usually have a camera pointing at me in my office. If you go to my webpage, you can see that. So usually people look at the camera to see if I'm working or talking to somebody. If I'm talking to somebody, most likely it's not a good time, that sort of a thing. I'm also on AOL chat most of the time, especially later at night. So that's an easier way to reach me than trying to meet me in person, right? Or if you want to send email, if it's sort of general questions, send an email to the class list so everybody can kind of follow along, right? So before we start, some preliminaries, right? So we will read papers. So this course is organized as a graduate level operating systems, not as undergraduate level operating systems. So I assume that you have taken undergraduate level operating systems and you're able to sort of take that particular class which I taught in the spring. So I think I handed out the final exam from the spring class. Try to take it, try to see if you can answer those in some sense without looking at the book and all those things. I'm not going to do some tests to figure out if you're ready for the class. I'm just going to let you evaluate how ready are you to be in the class. I'm free to, I would work with you to help you get through the stuff. But remember, many of you may be taking this course as a core course, right? Which means that you're forced to get certain grades. I mean, if you probably are told the grade stuff, you need to maintain 3.5, which probably means that you have to get at least a B. Anything less than a B is not acceptable. It won't count towards your quals thing. The higher you get, the better it makes it for other courses and all those things. You probably know the drill. If you don't know, talk to the folks who've been here for a year to understand what's going on. So the bottom line is you at least should get A minus, which is probably what will help you, right? If you get a B, you need to get 2 A's in other areas, so which may or may not be easy. What that means is, if you're not prepared, right? So we're going to start reading papers starting from next lecture. If you can't read those papers, then you're probably not going to do well, right? And those papers assume that you at least know enough operating systems to kind of get to the point. I mean, those papers are beyond that level, which is where we are going to bridge the gap from that level to where the paper level are. I mean, these are the top papers in the field. But if you don't have the background to start discussing, so if you talk about how some thread scheduling mechanism works, and you don't know what threads are, you don't know what scheduling is, I can't go over those topics, right? So you can. There should be audio, video, and all those things from the previous lectures. Look over them. Look at your own background. See how prepared you are. I can't really help you if you don't have the background. If you don't have the background, the recommended way is for you to take the course and then come back the following fall. Right? Is that clear? How many of you have taken this course before at the grad level? I think there's a couple of you, right? So. So you know the deal. I mean, the qual system is meant to be easy, but it's still sort of tricky. So before we start, this is going to be a discussion-oriented class. I'm not going to lecture all the time because you have to read the paper, and I have to test how much you read the paper and stuff. So let's start with introductions, right? Little brief. I mean, just your name and what do you want to achieve. Previously, people typically say, "I'm forced." You know, they I don't want to be here. I would rather be somewhere. But that's okay. Beyond that, what do you hope to achieve with this stuff, right? And something about your prior operating system experience. It's okay to say I don't know much about operating systems, but I just want to get a sense of where people are, starting from, I guess.
Well, I'm Jerry Kruzek, and I got a bachelor's in electrical engineering from Notre Dame several years ago. Worked on a master's in electrical engineering at the University of Illinois and have an MBA from, I hate to admit, the University of Michigan. My research interest is primarily networking and also especially security. I'm very concerned that we're taking a very defensive measure with regard to security in IT, and I'd like to see if there are some more aggressive ways that we can go ahead and protect our resources, which gets into one of the things I hope to achieve out of this class, is even a better understanding of operating systems to see whether we can do a better job at the operating system level of protecting our resources. In my home, I've got a collection of PCs. I've worked with Red Hat, I've worked with Solaris and the Windows operating systems, and I also go back to some mainframe operating systems. The OS is on IBM and MCP on Burroughs and that.
Okay. Let's keep that. Yeah.
I'm Andrew Ryder. I went to St. Edward's University in Austin, Texas, and I hope, I guess, just to get a better understanding of some of the fundamentals of how computers are operated, because I'm going to be working with computers a lot. So, and I'm interested in machine learning and pattern recognition types of things. So.
Hi, I'm Reena Thomas. I did my BTech in Computer Science and Engineering from Cochin University of Science and Technology. Well, my research interests are plant fuels in embedded system under Sharon Hu. And about this class, I hope I'll get to know more about the operating systems that I can use in my research field.
Hi, my name is Sean Liu. You can call me Sean. And I have an undergrad degree in chemical engineering. And I got my master's degree in computer science this May. So I came here for my PhD. So this is my first class here. Yeah, I never take any operating system class, but I like this thing. I like Linux. I like to compile a kernel or something. It's fun.
So you took a master's in computer science, but didn't take a operating system?
I had an undergrad OS in China.
Okay, okay.
Yeah.
Okay.
I think it's fun.
No, I was kind of surprised that they let you do masters without.
Actually, I was a TA for undergrad OS
Okay.
in Michigan Tech.
Okay.
So I came here. So
Okay.
I think I'm
Okay.
trying to qualify.
Hi, my name is Jim. I got my bachelor's degree in computer science from China. My research interest is medical image processing. I'm now working with Dr. Chen. I like operating systems. I want to know more about it.
I'm Chu Jai. I got my bachelor degree in electrical engineering. And right now I'm using the Linux Ubuntu. Sometimes I have some problem with my computer, but I don't know how to fix this problem because I got my degree in another department. So yeah, I want to take this course and get some knowledge about the operating system.
My name's Ryan Hoens, and I'm from Rochester Institute of Technology. That's where I did my bachelor's and master's. My research interests are somewhere between everything, security and data mining. I hope to achieve in this course is to become more fluent in the concepts that are important to OS, which actually have many parallels in other fields. And yeah.
Hi, my name is Mehrdad. I got my bachelor degree in electrical engineering from Sharif University, and my research interest is mainly cryptography and information security. I hope I can get to know about the operating system and can take advantage of my knowledge in this course to how to protect our systems as an application of computer security. And also I know how to work with Windows and a little Red Hat.
I'm Mike Olson. I got my bachelor's in math from St. Olaf College in Minnesota. My research interest is in bioinformatics. I think in this class I hope to get the kind of knowledge so that when I fix things on my Linux boxes at home, that I will know what I'm doing rather than just blindly copying what somebody else wrote down I should do on a message board. I have tried to migrate from Windows to Linux about 4 different times with different distributions and failed almost every time. But I'm going to try Ubuntu pretty soon now, and hopefully that's been easier in my experience, so maybe that'll work.
My name is Juan Bu, and I work with Dr. Tang on distributed scientific database. So I work with Condor a lot, so I need to understand system programming. That's what I want to get out of this course. and I guess we get this course to Bachelor. So.
My name is Sarah Baker. I went to George Washington University, and I'm working in biometrics and Dr. Lawyer on iris recognition. And to be on this class, I like to learn more about operating systems and how to use it in my research.
Hi, my name is Jim. I did my undergrad from National Institute of Technology, India, and my research interests include pattern recognition, machine learning, data mining, those kind of things. I have some experience working with various flavors of Linux and Windows. So my intention from this class is to deepen my knowledge more on those in order to help in this.
I'm Nate Rowland. I got my bachelor's degree in 2007 from Notre Dame in computer science. I'm currently working in experimental systems on a collaborative file system for laptops, and those who know me know that I haven't encountered too many computers in my apartment. I have Windows 2003 server, XP64 workstation, some Red Hat machines, FreeBSD, router, and some other things. So I like operating systems a lot. I hope to get out of this class a different perspective on operating systems, perhaps increase my understanding of timing and synchronization and some of those things.
Hi, I'm Mia Jarikin. I did my bachelor's in Bangladesh University of Engineering and Technology, and I did my master's in University of Texas at Dallas. Though I took the operating system, grad operating system in UT Dallas, but I saw in the website that this course material is very different from that. So I hope to learn from this course, and my research interest is in algorithms and database systems.
Okay. So one of the themes I get is we want to know more about Linux and Windows and all those things, right? Unfortunately, you'll find that we're not going to do that, right? We're going to do very little of, I'm completely agnostic about what operating system you use and stuff. One of the main things about operating systems that you guys have to I hope that you will understand after the classes, it's all about trade-offs, right? At the basic level, operating systems is all about managing trade-offs, right? Which means that you can either do A or B. A is good for something, B is good for something else. You can either run out of main memory, or you can have this concept of virtual memory where you move something to the hard disk. So you can run bigger programs, but you run slower, or you can run faster programs without virtual memory kind of stuff, right? So it's always about some trade-off. It's never about one absolute technique. So each of those may be implemented in your favorite operating system, Mac or Linux or Windows. And I have my preferences on what I would like on my home PC, what I would like to do for research, what have you. And each one has its own pluses and minuses and stuff. But that's not what I'm going to talk to you about. I mean, I'm not going to say Linux is really the bomb because it can do something, right? Because the reason is for a certain problem, you have to do some trade-offs. And each one chooses a different trade-off, and each one has a different implications because of that, right? The way it applies, the reason why this is a core course is, regardless of what you do, if you use our computer to do something, you are going to fight with what the operating system is going to do, right? Operating system is running as the supervisor for your machine, right? It lets you reach the hardware. So somebody decided that certain trade-offs are good for you, right? So for example, they may have decided that small processes are what really happens, and they're going to optimize it for that particular stuff. So you need to understand what exactly the trade-offs are being done, what the implications are. So you can either decide to fight against it or work with it, right? If your machine is designed for small programs, right, and you decide to write a really large program, you're basically trying to fight the trade-off that it's designed for, right? And you'll see really awful performance. So if you took the undergrad OS class, one of the things you do with the paging and all those things, if you change your row major order matrix to a column major order, it has a drastic difference in performance because of the way the memory systems and all those things work, right? So that's what I hope to go through in the class. I don't particularly care what Linux does or what FreeBSD does, but I want you to understand what are the challenges and how it affects what you will end up doing, right? Because whether even if you never look at the operating system ever again, you are forced to deal with it because the decision that they make affects you, right? And that's one of the reasons why we're going to read a lot of papers, but we're going to discuss them to understand what are the decisions that they made, why it was made, and how it's going to affect you. And you'll find that a lot of the things that you thought you knew how to use, you don't really understand. How many of you use AFS, the file system we use at Notre Dame? How many of you use NFS? How many of you use NTFS, distributed file system? How many of you use NTFS? Right? So you must have used some file system, right? I mean, I'm throwing all the names I can come up with, right? How many of you understand what's the cache coherency protocol that is being used there? And how many of you understand what that does to you, right? So what that does is, for example, we'll see this later in the class, AFS does last writer wins protocol, right? You may not know what that means, right? But it has a very significant impact on what you can do with it, right? With AFS, you cannot write a database on the AFS server, right? You need to understand why, right? The answer is not a trivial, because it just does not support it, because the protocol that it's doing, it's optimized for something else, not for what you're trying to do, right? And that's what I hope to tell you in the course. That's the thrust of what I'm going to go. So if you expect that at the end you will know how to use Windows XP better than you know now, you'll be disappointed, because I don't particularly stress that, right? Now, of course, we have 2 course projects, and you're free to explore some of these things, and you're free to go into one of those things, but keep your mind open. I mean, the particular operating system is not that important. The concepts are more important, right? So today I'm just going to talk about the course organization, expectation, and so on and so forth, the logistics of the course, and the honesty rules and stuff. The first one is we'll read seminal papers, right? I think seminals is in quote because I think there's a lot of issues on where the word comes from, right? But anyway, these are very important papers, and I usually try to pick them from conferences such as SOSP, OSDI, HASPLAS, and TOGS, right? So the sort of the best computer science, the operating system conference is SOSP. People would argue OSDI is similar too, and they are biennial. They happen every 2 years, right? And they usually accept like 18 papers or so, right? So these, and after they go through this conference, they eventually end up in TOGS, which is the journal version. So what that means is, on average, each paper, the authors might have worked on it for 2 years, right? Before they publish that one paper, if they're lucky. I mean, they work on it for 2 years, they're lucky, the paper gets accepted. And then after a year or so, it goes through TOGS, right? So they probably worked on it for 3 years on just this paper in 15 pages or so that is being assigned to you, right? So don't expect it to be 15 pages like a novel that you can kind of read through and stuff, because this is all, so all of you are on a PhD program. So imagine for the next 3 years you work on something and you're going to write everything in 15 pages, right? So it's not expected to be easy to read, it's expected to be dense, because I don't know how many of you realize this. Is it easy to write a 100-page paper or 5-page paper?
Depends. I mean, the 5-page paper, if you're looking at something to be completely detailed and concise, that's, I think, a lot harder.
The undergrads usually say 100-page paper. I mean, the 5-page paper, right? Because they're like, I can't write 100 pages, right? It's easy to blab on about 100 pages, right? Because you're not rigorous in your thinking, because you feel like you have all the space, you kind of try to fill up with all the thoughts you have. But when you're writing a 5-page paper, you have to lay out your arguments precisely, right? So every word counts, because any of you write the paper, right? When you start writing papers, you figure that the page limit is your sort of your enemy, right? So you have to kind of find the right word to say what you have to say. So each word means something, right? So you have to try to understand what each word means. You can't just read it and say, I don't know if they really meant that, because everything there they meant it, right? But on the other hand, this is sort of the cream of the crop. So it's things we need to do. So I have to force you guys to read it. I have to force you guys to read it to fully understand what's going on in the paper. And I actually handed out one thing on how to read the paper. I'll talk about that in a couple of slides. There are some tricks that you use to read those papers, right? Regardless of what, it's not going to be easy, right? Especially how many of you have read research papers in grad school or undergrad, I guess? Few of you, right? And so for people who have started to read the papers, you understand what I'm talking about. For people who haven't read the papers, you probably don't understand, but you'll see very quickly, right? Papers are written in a certain fashion, so it's very easy if you follow that pattern. If it's very hard if you go against it, right? What I mean go against it is take a paper, read from start to end, right? If you can stay awake and read the whole darn thing, you are great, right? But you have to go beyond that. You have to understand what they're trying to say and try to incorporate that into your thought. So when you do this stuff, when your advisor asks you to get some files on AFS, you have to be able to say, well, I can't really do that because this paper, so the paper is not going to talk to you about what the decisions they made will affect your project, right? They're going to talk about, they're going to sell the project. So they're going to say, this is how we did it and this is the best way to do it. They're not going to point out their weaknesses beyond what they would like to concede at some point. They're not going to say, AFS is really, really awful for what you want to do. They're going to say, AFS is good for precisely what we define. If you don't understand so you need to be able to understand what it is good for and what it is not good for, which is not in there, but you need to try to understand those. And I want you to incorporate that into your collective knowledge, which is the reason why it's a core course, right? And so you're not trying to understand it not just for understanding what's going on, but I want you to get it into your bones what the trade-offs that are being discussed there, right? So usually you'll find that discussing the paper is very hard. I'll give you hints on how to read the paper. But usually what happens is it's good to discuss it with people, right? You can kind of say, this is what my understanding is. Somebody says, no, my understanding is different, right? Either because they read it differently or because everybody has their own background. You come from a different background, you have their different operating systems and all those things. So you read something different from it, so you would have to do the discussion. So we're going to discuss this in class, but unfortunately the class is only an hour and 15 minutes, so we can't go through all the stuff. So I want you to read the paper. We'll give you hints on how to do those stuff, and then collaborate with amongst yourself and try to understand what the paper is talking about, right? So be sincere about the discussion. This is not designed for. There are no grades for reading the paper because the course depends on the stuff, so I don't have to kind of test whether you read the paper. You notice it from other stuff. And even after the warnings, I see people don't want to read the papers at some time. So I'm going to have to put some rules. One of the rules is you have to email me something, as a little text of what you thought the paper was and what you liked about it and what you didn't like about it, right? You can send it to me as one email message. You don't have to send one for every group member. And as we'll go through the honor code, you have to tell me who all discussed this, right? I'm not going to evaluate it. This is basically for you to kind of tell me what you've done. And I want this like 5 p.m. the day before the class, and for Tuesday class, Monday, and so on, just so that you have time to think about it, right? I don't want you to come into class at 10:55, send me the email, and not be able to digest it, right? And most of the things you'll realize that for me, when I take a shower, it kind of like sinks in. You kind of like thinking about something and then kind of sinks in. So I want you to go through the stuff. The other catch is you are free to discuss it with your friends right up till the class, and we can discuss it in class. And after that, you're not allowed to discuss it till the homework is due, right? I'm going to give you homework assignments based on those papers. So if you didn't bother to read the paper and you didn't ask the right set of questions at the classroom to understand what is being discussed, then you're kind of setting yourself up for a tough time reading the paper all by yourself, right? So is that clear? So form as many groups as you want. I'm not going to insist how many people should be in part of a group. And if you have groups where somebody is not doing their work, you're free to work with them or not, because there is no penalty for not wanting to learn. You don't get the grades at the end, right? But otherwise, use these kind of resources as much as possible, because as you will find, you don't always have the time to read all the papers. You don't always understand all the concepts. And these papers I can guarantee you, they're not necessarily the most easy to read. They're easy to read once you know what you're doing, but I'm assuming that that's why you're here, right? So does that make sense? So I can't stress enough of this. If you don't read the paper, then what I say in the class would just go ahead. I can't possibly explain all the nuances to you. And it's not about what is in the paper. It's about what is in the paper and what it means in the larger scheme, right? And we'll see what that means, right? So course project, right? Traditionally, operating system courses have a course project. They have to, like a one large course project. People have taken courses elsewhere. Here, you tend to have like 50% of the course for a course project. You have one large course project and stuff. I'm trying something a little different here, right? This is based on the observation that most people don't start on the project till the very end, and then they try to cram something up, and then it's kind of you turn in something. But the real bottom line is, the project, I expect you to have a report and a presentation, right? That's part of what you're going to do all your life in the grad school, but at least I want to stress a thing. If I have one course project, I can never give you feedback. I can tell you what you did wrong, but I can't really see you kind of fix those, right? So you're going to have two course projects, which is really one course project split into two projects, right? And it's a group of 2 projects. If you want a larger group, talk to me. I'm flexible on what you want to do. If you have some idea that you want to explore, talk to me and you can go with that. For people who don't have idea what they want to do, I'm going to have 2 projects, right? I'll say about this in a little bit. But first, what the project is not, right? This is not a programming project. I'm not trying to see how good you can program, how many lines you can program, whether you can program in C, Java, Perl, whatever, right? That's not what this course is about, and that's probably not what your advisor cares about for your own research. You don't say, my research idea is not that good, but I wrote it in 10,000 lines of Perl, right? Which may be achievement, but that's not what I care about, right? So all I care about is you write a report. 6 pages is, I think, what I had. In some readable format, don't use like 1-point font to turn in the report, where you describe what you did and what you learned, right? I don't particularly care about the programming language or operating system you use and all those things. And I'll show you a little bit what kind of resources we have for you to do this stuff, right? So you can either do the project that some suggestion I give, or something that helps your research, what have you. But I want it to be 2 projects, so you can submit a report on the first one and give you feedback for the second project. I hope to see improvement. For the presentation, I hope to see improvement. What I'm looking for is for you to understand what problem you're trying to solve, and why it's important, why I should care, and what is the intuition behind what you're trying to do, and why you hope that it will work, right? And why you hope that you'll find a solution. It's not that important whether you actually find the solution or not, because it's a month or 2 project. So I don't expect you to come up with something that is publishable. It's good if it's publishable, because most of you want publications and stuff. But the key here is for you to get through the process, not necessarily the output, right? Which means that you don't have to be novel. I don't care about novelty. So you can take some paper that you like and you want to repeat the same thing, right? In the same exact setup or something a little different or what have you. I'm not looking for novelty. I want you to do the same thing, right? I mean, of course, you can't copy the results, but if you find a paper which talks about they did this for desktops and I want to do it for the desktops here, that's perfectly fine. You can do the exact same stuff that people did, but I want you to think of why, because I'm going to ask you why you did that. Why did you? What came to your mind to do that, right? So the most important part is why. The least important part is the programming part. So that means that if one of you is not very good at programming and somebody else is good at programming, they would be ideal project partner, right? So hopefully one will do something, the other will do something, they complement each other. Having a large program is not exactly the one way to get a good grade, because it's not a programming class, right? So the way I split that is, first one, you measure something, right? Because most of the systems, when you want to do trade-offs, you have to understand that there's some problem, right? So you need to kind of measure the system. And I'll give you some examples of, I think, the web page. So you measure something, right? There's tons of papers on measurements. We'll read some of them later in the course. So for example, people want to say, how are these lecture PCs being used, right? Are they used, like how many time are they used? How much time do I leave it on each slide? What is this machine being used, and all those things, in order to optimize something for this machine, right? So the first step is to understand what these things are doing, right? So for example, this machine may so happen that their primary goal is to be a PowerPoint lectern, right? So you want them to go to the next slide when I press the next slide fast and not be bothered by something else, right? But you may find that as a Windows XP machine or Windows Vista machine, it may be doing stuff, like it may be backing up when I'm trying to change the slide. So you want to understand whether it's actually a problem and how to fix those kind of things. So the first project, you will measure something. Second one, you'll try to fix those. And again, I'm not trying to don't make it too hard on yourself on coming up with SOSP style work within this course project, right? Because it's just not, it's way beyond the scope of what we want to do. So don't kill yourself coming up with the best idea, but it's okay to kill yourself to try to understand what small thing that you come up with, right? To understand why it's interesting, what do you hope to achieve, and things like that. Think about the depth of what you're trying to do, not aim too big, right? And again, you don't submit the paper, the report. I want it to be 6 readable pages. There's like the number of different style sheets that you will probably use in your own career. My thing is, make it readable. I have glasses, so don't put it in 1-point font and stuff like that. So we have a number of resources. We have a bunch of machines in the Cushing 208 lab. I think if you ask Jenny, she'll give you the code for the room. So there are 6 machines, 6 desktop machines, 2 ITNM machines, and a bunch of other machines that I can get you for this class. This lab is designed where you can do whatever you want with them at the software level. You can install your own operating system. You can do whatever you want. The only restriction is you cannot break hardware, right? These machines cost money, and we don't have infinite money. And you are not. So if somebody else is working on it, please ask first, right? So if your friend is working on it, just don't reinstall the operating system right on top of what they're doing. And you're not allowed to do illegal stuff, right? So that's a sort of nebulous concept. So what you do may turn out to be illegal. Maybe somebody will complain. So my promise to OIT is if what you do turns out to be illegal incidentally, I take responsibility. If it's intentionally illegal, then I'll come after you, right? For example, if you're trying to see how many packets you can send before the CTO's Windows XP machine will crash, I don't see what's the research potential on that one, right? So if you're trying to crack into my desktop to see what your grade is or what have you, I don't see what the research in that one is, right? So if you do those, clearly you'll have to suffer the consequences. But if you send some packets which went somewhere and then somebody complained, I'll take responsibility for that. So you're free to do whatever with this machine. So this is a good way to try things out. You don't have to worry about hurting something. You don't have to don't do this on your own laptop and lose the machine for something else, right? So that's an important step. So again, I come from this sort of a systems philosophy. I tried to put this slide up because this is sort of where these papers that you'll read come from, which is people like to see that the results come from your own implementation, right? That carries a lot more weight than when you say it comes from a simulation. It carries more weight than if you see it from some other paper, if you see it from simulation from some other paper. And the last one, which everybody does, including people who are in systems, try to do is they say, I think this is what should happen. How many of you use that word? Many times you may realize that you're saying this, and many times you may not realize what you're saying this, right? I see people say, but it should do that, right? I mean, if I connect my laptop to this projector, it should display the stuff, right? You say this stuff all the time, right? You think you know your computers really well because you just think you do, right? But many times, reality stares back at you, and I see people constantly say, but it should do. I mean, like I tried it in my lab and it worked, and it should work, right? Usually it's worth nothing, right? Because you have to, if your implementation shows something otherwise, then I believe that, not what you think should happen, right? Including myself. So if I grade something, if I say that your answer is wrong, and if you prove me wrong by implementing something, then you win because, hey, that counts more than whatever, right? But the key thing that I want to stress is, just because you implement it and you have no idea why it works, if you say, I don't know, I mean, just throw out this program, it seems to work like magic, that still counts as this one, right? Because we don't deal with magic here. So you need to kind of understand what may be happening, form some hypotheses and test them to the extent possible, but at least have some reason why something may or may not be working, right? Does that make sense? So the course grades, so I'll have an exit interview with each of you for 10% of the grades. Basically, I want to try to see how well you understood the projects and how it ties with what you did, kind of stuff, right? The midterm and final exam, midterm is 10%, final exam is 20%, take home, open book, open notes kind of things. And assignments, there are 6% each. Essentially, the course is divided into 5 different sort of modules. If you look at the course page, there are 5 different modules. Each one of them, after the end, I'll give you a homework assignment, take home, sort of in what we did. And so you have 5 of those. So essentially, this and this component is based on the papers, right? The concepts in the papers. The projects, 2 of them, I can't do math, but there's 30%, right? So third is for the project, and the rest is for homework assignment and the exam, right? The exams are time bound, and the assignments are not time bound. That's the sort of difference, right? And ideally, since this is being a core course, you would if you ever challenge what you learned in this class, and if you think that the course grade you got was not indicative of what you learned, you would probably contest it by showing the final exam and say, hey, look, I showed that I understood everything in the paper, kind of stuff, right? So that's the grading scheme. Are there any questions about how are we going? I don't follow the usual 90% for A and all those things. I kind of look at the how the class grades are turning out, right? So if there's a big difference drop in some grades, so if there's a bunch of you in 95 and then the next bunch of you is in 85, then it's clearly the 95 should be getting some grade better than the other one. I usually don't go by half points or something. So if you got 90% and somebody got 89.5, I don't like to say the 89.5 should get a B or something, right? So some other details, more details are on the web page. So essentially, if you reevaluation, so we don't have a TA for this class, so I'll be grading those stuff. If there's a mathematical error, is clearly you get the points. If it's a partial credit, right, then I'm giving the partial credit hopefully by looking at all the stuff that people did. So if I give you more points because you think your partial answer deserves more, then I have to reevaluate the whole class, right? So I have to give you a penalty for you to challenge it, right? So that doesn't mean that you can't talk to me. Talk to me to try to understand. So if what you wrote is not what I think you wrote because of the way things are written, then it's clearly something we can discuss. If you have some proof, like implementation or simulation or somebody else's simulation to show this paper showed this, so that's why my answer is true, then clearly you win. If it is just hearsay, you think that you deserve more points, then you have to give me in writing why you think you deserve more points. And I have to evaluate that based on, it only applies to partial credit, right? So the problem is, I probably did the whole class based on that, whatever criteria I had. So rather than me going to the whole class, I'm going to make you do work to convince me that you deserve more points, right? Most of the time it's not a problem, but if it is, then this is what we'll do. And lateness policy, there are no submit it at the time, right? So the homework assignments, drop it before the class, and the 5 p.m. Deadline for the reviews, right? Except for unforeseen emergencies, right? So foreseen emergencies are not acceptable, right? And you will see where they turn up, right? So some people say, I have to go for a conference, and the conference happens to be on the day that deadline happens. That's a foreseen emergency. I mean, unless you just took the flight and left right before class, you should have sent me email. We could have worked something out. I'm fairly flexible if there's a good reason for it, right? I'm not very flexible if you have no good reason for it, right? So if you're going to a conference, you should at least have the courtesy to let me know that you're going to be in a conference on the day. So you should make efforts to either email me the report or what have you, right? Don't come back from the conference and say, well, by the way, I was in a conference, I couldn't submit the work, right? You're just a grad student, so I don't have to tell you the details, but it's just there. So collaboration is acceptable, it's encouraged, except for the little twist I had to say for making sure that you read the paper, right? It's okay for you to talk to any of your friends, because in fact, I strongly encourage it, right? Because that's how you learn these things, because you'll find that what I consider as the right answer for something, you may completely disagree with me, and you may be completely right, because you're coming from a different perspective of how you do things. So like some of you who mentioned cluster computing and stuff, they have a set of assumptions which are different than what distributed systems in the AFS kind of setup do. So what they consider to be accurate and correct may not be what I would have naturally thought it is because of different assumptions, right? So the more you discuss with people, the more you realize that whatever you thought was absolute truth is not that absolute, because it depends on assumptions that you couldn't articulate before. And so you have to collaborate with other people. But as in any paper that you write, you have to give credit, right? If you don't give credit, in this class, I consider that to be cheating, right? In professional circles, if you don't give credit to a paper, you are black marked. You suffer far worse consequences than I can ever do, right? If you write a paper where you stole somebody else's idea, your career takes a significant hit, right? It doesn't take any hit at all if you say, my work depends on the discussion I had with the entire class, right? It does not diminish your work at all, because I'm not going to take away points from you for discussing with others. And the way I do that is through the Gilligan's Island rule, right? It's a long thing, it's the web page too. But the idea here is I want you to discuss to understand what's going on. I don't want you to discuss so you can copy the answer, right? So discuss all you want, but I want it to settle in. So one of the rules you do that is to watch TV, right? So that's one reason I want it to be like 5 p.m. So if you send all the stuff, if it sinks in, if I ask you something, you know what you wrote, right? If you had a discussion, when you have a discussion, you're not allowed to take notes, right? So you discuss the problem, you go home, do something, and you write down. Whatever you write down is what you understood, what you did. So those things look like it came from you because it has your knowledge to it. If you don't follow the rule, then essentially it looked like you all had the same answer. That's not acceptable. Except for the summary, you can send one summary for the whole class. But in the class, if I ask you, so what do you think of the paper? I don't want all the group members to parrot the exact same talking points, because this is different. Does that make sense? Right? At the end of the day, when you finish the OS project, if some other faculty in the department says something about, so what do you think of the AFS consistency model? Hopefully you'll be able to say something intelligent and smart, right? And not like, I have no idea, right? It's not gonna look good on me, and most importantly on you, right? Are there any questions about the logistics so far? So how to read a paper, right? And actually, the one-page handout you have is excellent, right? I mean, this is the collective knowledge from the community for a long time, and people kind of added to this one, right? The main reason you're reading a paper in this class, because I told you so, right? And you need a grade or whatever. But hopefully the real reason why you read the paper is you're trying to understand what they're saying and what that does for you. Like, how is it going to help you, right? So the reason why people write papers is they want to get papers accepted so they can graduate, get a PhD, move on, do fun stuff. The reason why you're trying to read a paper is you're trying to see how is that going to help me, right? So you have different goals. They want the paper to be accepted, so they're going to say this paper is the best paper you can ever imagine because we have this problem and we're going to discuss this. So they're not going to critique their own paper. They're not going to say this is the problem we can solve and this is why our paper is really awful. This is all the reasons why you should not trust our results, right? Nobody's going to do that because, as you realize, it's not going to go anywhere, right? So they're going to talk about what is good for them, and you have to be skeptical. Regardless of how good the paper is, regardless of what it is, you have to be skeptical. You have to look at each decision. So they're going to say, our decision is we made a right turn because of, they'll give you reasons, right? That doesn't mean that, just because they can try to convince you that that's the right decision, does not mean that I want you to be convinced, right? Because they're making a decision at that point, and whatever decision they're making probably helps their system perform better. But you have to understand what happens if you take the other route, right? And maybe in your system, when you come up to do something, you may have to take the other path. So I want you to be completely skeptical. People write the paper as abstract, which traditionally tends to say everything about this paper, right? If you don't read anything, you should be able to read the abstract and understand what the paper is talking about. Then they give an introduction, motivation, problem description. They may be part of one section or what have you, where they try to tell you why this problem they're trying to solve is important and why you should care. And then they have a conclusion in future work where they sort of repeat what they said, right? The reason why they have to motivate you is most of the problems in systems, in operating systems, are made up, right? I mean, it's not inherent like a math problem or something. So you have to convince me that this is a problem that needed to be solved, right? So you need to convince me that this is a problem that's what was solving. So for example, if your motivation is I want to run Windows 95 on my desktop, would you think it's a good motivation? Because it depends on the time frame, right? So for you right now, it's like, why, right?